Good morning. Today we begin a new chapter. This is on plastic deformation of pure metal. Last class we looked at evolution of microstructure of pure metal, and the metal that we use, they are made up of several crystals, they are oriented at random, and its properties will depend on the type of crystal of which it is made up of, and it will also depend on the way these crystals are arranged in the metal. And today we will look at what happens if we try to deform the metal. Now, we will look at the types of deformation. Broadly, the deformation can be classified into elastic and plastic deformation. The elastic deformation is reversible. It remains as long as there is a state of stress present. Once you remove the stress, the material comes back to its original shape and position, or shape and size. Now, plastic deformation on the other hand is permanent. Even if you remove the stress applied, it is only the elastic part of the stress which disappears, but the permanent deformation remains. Now, we will look at critically the mechanisms of plastic deformation of pure metal, and we will try and find out at what stress actually the deformation, permanent deformation takes place, and what is the nature of this stress, what type of stresses can cause plastic deformation. We will also look at the stress strain behavior of typical crystals, say particularly face centered cubic crystal. We will also try to find out an estimate of the theoretical strength of an ideal crystal. So, basically these are the 4 topics that we are going to consider in this chapter. Now, to recapitulate the difference between elastic and plastic deformation, you are already familiar with this type of stress strain plot, which we normally perform to find out strength of material, and we looked at it in detail and the type of information that you get from this kind of test. Now, this part of the stress strain diagram represents elastic deformation. If you deform a material here, unload, it will trace back its path and come back to its original shape and size. But if you load it beyond this point called proof stress, then if you unload, it will only the elastic part will get recovered, but there will be a permanent strain left behind, and this is schematically shown here. Elastic, this is the nature. If you apply, there is a deformation, but once the stress is removed, it comes back to its original position. So, this is reversible. On the other hand, plastic deformation, if you apply the stress, you go somewhere here, you remove the stress, that permanent, that deformation remains, only a small part which is elastic is recovered. So, this is permanent. Now, obviously, if you look at the mechanism of deformation, what happens with respect to the crystal structure? We have seen that strain is defined as stress over Young's modulus. This is the Hooke's law under uniaxial tension. So, in terms of crystal structure, so you have, I have just shown a 2D crystal structures, and if you apply stress, what happens in one direction, this direction it elongates, but in this direction there is a contraction. So, basically you have strain in 2 direction, in one direction, in the direction of tensile load there is an expansion, whereas perpendicular to that there is a little contraction. So, therefore, even though stress is uniaxial, you have strain in this direction as well as perpendicular to the plane. So, you will have three component of strain, and if you have a system, if you can measure, we have seen the how extra diffraction can be used to measure the lattice spacing. If lattice spacing is measured, then the change in lattice parameter can be converted into strain, that is change in lattice parameter delta A over that initial lattice parameter A. So, this is strain. So, that means extra diffraction can be used to find out the extent of elastic deformation or the presence of stresses in metals, residual stresses in metal. Now, it may be worthwhile to understand deformation. We have to know what kind of stresses will actually be responsible for deformation. So, for that it is just to recapitulate, people having background of applied mechanics will know how stresses and strains at a point is represented, which is shown here as a unit cube, and with respect to this x 1, x 2, x 3, this is a set of orthogonal axes. This represents the state of stress, this represents state of strain. Strain is represented as epsilon I j, let us say, and I can have any value from 1 to 3. Similarly, j can also have 1 to 3. For example, this epsilon 3 represents normal strain on plane which intersects S3 axis at right angle. So, this is the plane which intersects, which is normal to x3 axis. So, this is the normal strain. You also have strain in this direction, which is called shear strain. This is this acts on plane 3 in direction 2. So, along this direction, and the same way sigma 3 represents the normal stress on the plane which intersects x3 axis at right angle. Sigma 2 is shear stress along x2 direction acting on plane which intersects, which is normal to x3 axis. So, therefore, the state of stress can be represented in the form of a matrix like this, sigma 1 1, sigma 1 2 is a 3 by 3 matrix, and also you must remember that state of stress should be such that there should be a state of equilibrium. So, that means if there is a sigma 3 stress acting here on this plane, there should be a stress equal and opposite to the other side of this. Similarly, the torque which is generated by sigma 1 3, and this is also 3 1 1 3, and this is 1 3, this is also 1 3. This is the torque generated by this should be balanced by the torque generated by the sigma 3 1. So, basically, so that means sigma 1 2 or sigma 1 3 should be equal to sigma 3 1. So, in reality it is good enough to define stress. So, that means the stress matrix is symmetric. Sigma 2 1 is equal to sigma 1 2, sigma 1 3 is equal to sigma 3 1, sigma 3 2 is equal to sigma 2 3, and same thing happens in case of strain as well. So, you have 6 component of stress, 6 component of elastic stress, 6 component of elastic strain. Now, advantage of this kind of matrix representation is helps you to transfer the state of stress from one reference axis to another reference axis. Very often those who are familiar with stress analysis, they will know that stress at a point can be defined with respect to a reference axis. If it is defined with respect to one reference axis, and often you have to determine stress with respect to another reference axis, then what you need to know is the direction cosine between this old reference system and the new reference system. If these direction cosines are known, it using tensor representation very easily state of stress can be converted from one reference axis to another. Now, let us look at few very common state of stress. Like when you do a tensile test, you subject the specimen to uniaxial loading. You have stress only in one direction, that is sigma 1 and rest of the components they are 0. You can also have a situation where the stress, say this is S and this component is minus S. This type of stress actually represents a case of pure shear. What does this mean? It means there is no tensile component, it is shear, and later on we will see it is this shear stress component which is primarily responsible to cause plastic deformation in pure metals or crystal. If the state of stress is like this, you have only these three normal components, that means all principal stresses, this normal component, this diagonal component are also known as, if these diagonal components only exist, rest of these are 0, then one can call them as principal stress, and this reference axis is described with respect to the three principal stresses. Now, if all the three principal stresses they are equal, say in this case this is P P P. So, this means this is a case which is something like you can say a state of hydrostatic stress. So, if it is minus P minus P minus P, that means you are trying to compress a particular solid from all direction. Now, this kind of stress, state of stress, that hydrostatic state of stress cannot cause any plastic deformation, because under this condition, if you convert, if you try that reference axis, try to find out what is the state of what kind of shear stress you will have, you will find all the shear stress component will be 0. If there is no shear stress, the material cannot undergo any plastic deformation. So, it is important to know the state of stress, because very often although a simple tensile test you subject the material to uniaxial stress, but for deformation often you will have multiple stresses applied along different direction, and you should be conversant, one should be conversant with the state of stress which can give result in plastic deformation. Now, using this kind of representation, as I said, that sigma I j and epsilon k L. So, suppose this is the state of stress, epsilon k L is the state of strain at a particular point. These two are related by a relationship like this, and in inverse of this is strain is related to stress by this. So, this is the strain tensor, this is the stress tensor, and you also need another tensor which will convert one into the other. And this matrix S I j k L, this is called compliance matrix, this is called C I j k L is called stiffness matrix, and this kind of a representation also signifies that this is not just one term. See, I j k L they change from 1 to 3, and wherever these indices are repeated, like k appears here, k appears here. So, this represents summation over k, that k extending from 1 to 3, similarly L extending from 1 to 3. Similarly, you will have here also exactly same thing it indicates. Now, as you can see, so if these numbers each you change from 1 to 3. So, if you start writing this full expression, it will be a very long equation, and so one way, a convenient way of reducing it is to see that how many component of state of stress is important, and we have just seen that this stress matrix is symmetric. So, that means these off diagonal elements, they are equal. So, actually you will have the 6 component of stress at a point, sigma 1, 2, 3, and this is a CS stress component, which is represented, that is sigma 2, 3 is represented as sigma 4, sigma 1, 3 is represented as sigma 5, sigma 1, 2 is represented as sigma 6, and same thing is done with respect to strain. But to maintain that similarity, it is possible to show when you convert this kind of 2 indices to represent strain and 2 indices to represent stress. When you do and you convert it into just 6 indices 1, 2, 3, 4, 5, 6, in that case there will be some conversion factor, and which is listed here. So, this component, that strain component, this should be epsilon 6 over 2 is represented like this. In that case, you have 6 state of stress, 6 component of stresses, there will be 6 component of strain, and they will be related by a 6 by 6 matrix, and this matrix is called the stiffness matrix. C matrix is the stiffness matrix, and from this you can find out it is possible to show that symmetry, that is I said that sigma I j is same as sigma j I. So, these indices, they are interchangeable. With this, it is very easy to show that this kind of in this stiffness matrix, this component C 1 2 will be same as C 2 1. So, what it means is this 6 by 6 matrix is actually symmetric matrix. So, how many then elastic constants do you have here? So, you can count this. So, first row is 6, second row 5, this row 4. So, basically it is a sum of 1 plus 2 plus 3 plus 4 plus 5 plus 6. So, it will be 21. So, you can have actually 21 number of elastic constants, stiffness constants, and this is true. I mean, this is what you need to describe elastic stress strain behavior of crystals where you do not have any symmetry. For example, it is the triclinic crystal where there is no symmetry, and similar relationship also exists with respect to, you can say this is an inverse relationship. Strain is expressed as a function of stress. In that case, the matrix is like this, S 1 1, S 1 2, and this is called compliance matrix. So, now this elastic constant, that means you need a large number of elastic constant to describe the elastic state of stress in a material, and this number of elastic constant that you need for material which is which does not have any symmetry element, that is triclinic crystal, you need 21 elastic constant. But we are fortunate, we often handle with the number of type of metals that we use, they are mostly cubic, and cubic crystals have high symmetry, and it is possible to show using this tensor representation that if you impose the symmetry conditions, this number of these elastic constants that you need independent elastic constants that you need to describe the state of stress is reduced drastically. So, for example, what does it mean? A cubic crystal has a 4-fold symmetry, 3-4-fold symmetry. That means, if you try to rotate it about one crystal axis, say let us say crystal axis is usually represented as A, B, C, as has been mentioned. So, about A, if you rotate it by 90 degree, it comes to occupy exactly similar position. So, in that case also you can convert this matrix to that, and each of these elements they will be equal. By imposing this condition, it is possible to show that in case of a cubic crystal, you need only 3 elastic constants S11, S44, and this is I think is S12. So, there is a mistake here, this should be S12. So, you need these 3 elastic constants, and there is a relationship between the stiffness and compliance, and which is written here. So, in terms of stiffness, you will have C11, C12 and C14, and in fact, we are more familiar with this. This is called shear modulus. Basically, this is and also if you look at these elastic constants of different crystals, and you will find if this relationship is satisfied, if there is a relationship between say suppose a material is isotropic. By isotropic means it has same property in all directions. So, even if you rotate a crystal by any angle theta, in that direction you measure modulus, it should be same. So, to impose this condition also, if you impose this condition, you will find there is a further relationship between these 3 elastic constants, that means S11, S12 and S44, which is listed here. So, that means, and similarly similar relationship exists between the stiffness coefficient, and we are more familiar with Young's modulus, and what is how is this Young's modulus is related to these compliances with respect to a single crystal, like E is S11, 1 over S11. Poisson ratio, this is the ratio of, this is minus the ratio of S12 over S11, and shear modulus, the C44 actually represents shear modulus. So, there is a relationship, if a material is isotropic, there is a relationship between shear modulus, Young's modulus and Poisson ratio. And if one looks at the listed from handbook, that elastic constants of different crystals which have been measured, and if you look at that, you will find in case of tungsten, although it is a crystalline BCC, tungsten has a BCC, its elastic constants are such that it is the material that it is isotropic. Now, polycrystalline material, we have seen it is made up of several crystals which are oriented at random, and random orientation will even out the effect of the single crystal property. So, because of that random orientation, most polycrystalline material will exhibit isotropic property with respect to these elastic constants, and in fact, same will be true with respect to other properties which depend on crystal orientation. With this background, I think it will be worthwhile to look at mechanism of plastic deformation, because to cause the deformation you need a given state of stress, and it has been mentioned the state of stress which can give plastic deformation is shear stress, which is shown here. You have, I have a 2D crystal which is shown here. You can also visualize as if these are different layers of atoms. It is like a pack of cards. Say if you put a pack of cards, try and slide. So, that is a case of a state of shear stress. Now, what happens if you apply shear stress? If you apply shear stress, if it is large enough to overcome the lattice forces, it can move, a part of the crystal will move, this top part moves over the bottom along this direction. So, this plane on which this movement takes place, this mechanism is called slip. The plane on which this movement takes place is called slip plane, and the direction and which on the plane there will be a specific direction along which this displacement takes place, that direction is called slip direction. And here after this deformation, if you remove the stress, since it has come back gone to another state of stability, minimum energy, it will not come back, the deformation is permanent. And if you look at the crystal structure on both sides, the crystal structure they are identical, there is no change in lattice parameter, there is no change in orientation, there is no change in volume. If there is no change in lattice parameter, there will be no change in volume, and all atoms here, the top part which has slipped over the bottom, all atoms irrespective of its distance from this plane, the bottom plane on which slip has taken place, their distance, their displacement is identical. It is one atomic distance for each one of these. So, this mechanism is known as slip, and as been mentioned, it takes place on specific planes along specific direction. Now, is it possible to look at the slip lines in a microstructure? So, we are familiar with the microstructure of metals. It is made up of several grains, and if you try and visualize, say suppose a slip has taken place, it has deformed like this. Now, point is there is no change in orientation. Now, if you can look at the microstructure just after deformation without polishing, you will see a line here. But if you polish it, normally to look at microstructure, normally what you do, you will polish, grind off the surface, make it smooth, then you etch it with a chemical agent. So, basically since the orientations are identical, if you grind off, so this portion goes, there is no trace left behind. So, that means something like this. So, if you try and look at this phase microstructure, it will look both sides of the slip plane, the structure will look identical, you will not be able to distinguish. So, if you want to see slip traces, what you have to do? You have to polish the sample, deform it, and then look under microstructure. In that case, you may be able to see that some lines along which permanent deformation has taken place. So, that means what you do, you polish the sample. So, which and say even if you before you subject it to deformation, you look at its microstructure something like this, and you deform it, and then if you look, you will find that some lines marks like this appear after deformation. And different planes, if they are differently oriented, this orientation of these slip traces will be different. So, this is a situation, but if you polish it, they will disappear, you will not see any such lines. There is another mode of deformation which is called twinning. Now, what is twinning? This is shown illustrated here. Suppose this is a 2D crystal. Now, here also like slip, the deformation takes place because of shear stresses. A part of the crystal, what happens? It takes up an orientation which is related to the parent matrix in a definite way. That is, the twinned portion is just a mirror reflection of the parent crystal. Now, let us look at this process here, something like this. You can see these are the these are the original positions, and on this plane or on this plane a deformation, I mean a part of this crystal takes up a different orientation. This is the original position of the atom. Now, here this atom moves here, this moves a little more distance, this moves still more distance, and this distance is the same as the original lattice point. So, there is one here. So, basically this one moves, you can say 1/3 of the lattice spacing in this direction, this atom moves 2/3 and this moves 1 lattice distance. Now, look at the atomic arrangement across the plane. Look at this, if you join these, this is normal, and this distance and this distance, they are equal. So, this is a mirror image, a reflection of this. This is a mirror, exactly the similar relationship, every part. So, this atom which is further down here, so this is the distance and this distance, they are same. So, this part is actually a mirror image of this part, same also here also. That means, this point which are marked by red, they are mirror image of with respect to those which are marked as blue, light blue here. Now, this part of the deformed portion, now look at it, the orientations are little different. So, even if you polish, grind off the top, the atomic arrangements are distinctly different. So, therefore, here even if you grind off, polish, you will be able to see the twins. Here this part is the twin, this is the parent crystal, and there is a definite relationship, crystallographic relationship between this and that. So, twin has a different orientation, and displacement here in the twin zone is proportional to the distance from the twin plane. And twin also, like slip, it takes place on specific crystal planes along specific direction, which are listed here. For BCC, twin plane is 1 1 2, direction is 1 1 1. For HCP, the twin plane is, it is a prism plane 1 0 1 bar 2, twin direction is 1 0 1 bar 1, whereas in face centered cubic, it is the closed back plane 1 1 1 is the twin plane, and twin direction is 1 1 2. Now, let us look at slip a little detail. So, slip, as has been mentioned, can take place in crystals on specific plane along specific direction. Now, we are familiar with representation of crystal planes and direction, that means Miller indices. So, slip planes, slip system will actually be represented by a set of crystal plane, say HKL, and a crystal direction UVW, and this direction must lie, is a direction lying on the crystal plane. Now, cubic axis, they are orthogonal, and in orthogonal crystal there is a definite relationships, that's very simple relationships between the Miller indices of the plane and the Miller indices of the representing the direction, which is shown here HU, KV, LW. Now, the number of slip plane is here the 1 1 1, this is octahedral plane. So, this is shown over here, and this crystal, this is 1 1 1. So, 1 1 plane, there will be not one, there will be several of these 1 1 1 plane, and it is possible using this relationship, it is possible to write down the indices of the crystal or the slip direction quite easily, as has been mentioned here. There are 4 such slip planes 1 1 1, and if you try and look at this here, 1 1 1 is a plane. Now, you try and find out which 1 1 0 direction will lie on this. So, one direction which is written over here, this is 1 1 bar 0. Now, you substitute here, you multiply, this is 1 times 1 is plus 1, this is minus 1 times plus 1 minus 1, and this is 1 times 0 0. So, that means this satisfies this condition. So, also if you try this permutation and combination, you will find there are 3 directions which will satisfy this, and in fact, we are ignoring the direction like 1 bar 1 0, which is actually the same direction, but the sense is opposite. So, that means each 1 1 1 plane has 3 close packed directions. So, therefore, you will have 4 number of slip plane, and each slip plane has 3 such direction. So, the number of slip system in FCC is 12. So, same thing you can do it for BCC crystal, but BCC crystal, if you calculate this atomic density, here the close packed plane is 1 1 0. So, which is shown here, this is 1 1 0 is the close packed direction, and close packed plane, and the close packed direction is this diagonal of the cube. So, in FCC the face diagonal was the close packed direction, in BCC the cube diagonal is the close packed direction, this is 1 1 1. Now, you have to find out what combination of this 1 1 0 plane and 1 1 1 direction can, how many such combinations are there. You will be able to show easily there are 6 1 1 0 plane. So, there are 6, and in each, like in this case, there is one diagonal is this, if you join this, another diagonal is this, there are 2 1 1 1 directions. So, you have 12 slip system of this type, but if you do a little calculation, unlike FCC and HCP crystal, the atomic packing density in 1 1 0 plane and few other plane like 1 1 2 and 1 2 3, they are not very much different. So, therefore, very often this can also, these planes can also act as slip plane, and it is also possible, I will leave it as an exercise to show that on 1 1 1 2 plane there is only 1 1 1 1 direction, there are 12 such planes. So, you will have 12 slip system of this type, and if the slip plane is 1 2 3 and slip direction is still 1 1 1, and you have 24 planes of 1 2 3 type, and therefore, you will have 24 slip system of this type. So, you have a very large number of slip system in case of BCC structure. So, that is why if you look at if you do you polish a sample, develop the microstructure, then give it a deformation and look at the slip line, you will find this slip line here is wavy. Unlike FCC, the slip lines are straight, here the slip lines are wavy. This is primarily because of a large number of slip system being available. Now, hexagonal crystal is shown over here. Here the most close packed plane is the basal plane, that is represented as 0 0 1, and close packed directions are these This is a closed back direction, this is a closed back directions. So, the number of slip system here is 1 plane and 3 slip directions, but you will actually find that the third slip direction, say this is one direction, this is another slip direction, this is the third direction, but if you add this and this, you get this direction. That means, all these 3 systems, they are not independent, actually there are only 2 independent slip system. So, this is quite important to know. Hexagonal crystal closed pack structure, because of its specific arrangement of atom, it has a very limited number of slip system. So, that is why that as I go down little later, it will be clear, it will be much more clear, that is hexagonal crystals are difficult to deform because of non availability of slip systems. Often few other slip system also operate, these are prismatic slip system. So, that means you join this and say this or similarly or this. So, this prismatic slip, but the direction is still same, the direction is along this closed back directions, but so that means you need additional slip plane, also you need additional mode of deformation, that is twinning. Now, a quick look at the state of stress, because we have just looked at that stresses and strains, they are represented much more convenient to represent in the form of this matrix like epsilon 1 1 1 2 1 3. So, this represent a state of strain at a particular point. Now, the strain can have 2 component, it is elastic, which is recoverable, and plastic. Now, when we are dealing with large plastic deformation, we are primarily concerned with this matrix, that is epsilon I j p plastic. Now, if you subtract that elastic component from here, you get the plastics strain tensor or strain matrix, and here if you add this diagonal element, the sum of this diagonal element gives a measure of volume strain. And we have repeatedly, as has been mentioned, that during plastic deformation, lattice parameter does not change, crystal structure remains same, there is no lattice strain. So, basically, so that means there is no volume change. So, that means sum of this diagonal element is 0. So, that means in the strain matrix. So, therefore, you one of this get fixed. If you know 2, you know the third one. So, that means what you have? You really have 5 component of strains. So, 5 independent, and for each of these you need one slip system. So, you need for any arbitrary deformation, if you want take a crystal, give any arbitrary deformation, you need a large at least 5 independent slip system. And we have just seen that in case of a hexagonal closed pack structure, you do not have 5 independent slip system. If you consider only the basal plane, you will have 2. So, that is why more other modes of deformation becomes important, some other either some other slip plane becomes operative, or a twin deformation is a must for to deform hexagonal closed packed structure. Now, a quick look at little similarity and the difference between these 2 mode of deformation, slip and twin. Slip is a relatively gradual process, and it takes place on specific planes and directions. It takes place specific planes and direction. Twin also takes place on specific plane along specific direction. Here there is no change in slip, there is no change in orientation. Orientation of the crystal on either side of the slip plane is exactly same, whereas in case of twin, the orientation on the either side they are different, although they are related, one is a mirror image of the other. Then displacement in case of a twin is proportional to the distance of a particular plane from the twin plane. whereas in slip the displacement is same for all planes. Now, slip is a quiet process, whereas twinning is a noisy process, and a very common phenomena we know is tin cry. So, when tin is deformed, tin is body center tetragonal structure, and when it deforms, it twins and it generates sound. So, it is noisy, and it also secondly, this process, that process of slip is very slow. It takes time, of the order of millisecond for the deformation to take place, and this process is very smooth. The stress strain diagram, if you look at, there is no serration on the stress strain diagram if the deformation is due to slip. Whereas, in case of twin, this process is very fast, it takes place in microsecond, and the stress strain diagram shows serrations, something like the tilt point phenomena kind of thing. So, these are in short, this is the basic difference between the two. So, today whatever we have looked at, to sum up, primary some of these common modes of plastic deformation. Two common mode of plastic deformation, as we have seen, is slip and twin. Slip, it takes place on specific crystals along specific directions, and each crystal like FCC, it takes place along plane, on plane 1 1 1 along direction 1 1 bar 0. Similarly, in twin also it takes place on specific plane along specific direction. BCC also it has a similar type of slip system, but that number is very large. Here it is 12, here it is 48, and this has a marked influence on the nature, on the microstructure. So, basically you see in a face centered cubic structure, we have seen that slip lines in a polished sample. If you deform and look under microscope, you will find such slip stresses. Depending on the crystal orientation, they may be differently oriented, but they are straight. Whereas, same thing if it is a BCC, you will find say like this. So, wavy. So, wavy means this is one plane, this is another plane, another direction, this is another plane, this is another. So, it actually crosses over. So, there will be such wavy slip lines in case of this is FCC, this is BCC. Another important thing we learned, that slip on either side the orientation is same. So, if you polish it, the lines will disappear, it will look like this, the lines will not be there. Whereas, in case of twin, there is a change in orientation. Whereas, in case of a twin, there is a change in orientation, say something like this, and twin will have two lines, two planes, this is one plane, this is another plane. So, this is the twin, and in fact, the twin region is quite small with respect to the whole grain, and another thing is net strain here is much higher than the strain that takes place with a single that slip. And here even if you polish, and this will remain, because this has different orientation. And we also looked at the need for having a large number of slip system to give any arbitrary deformation, because we have seen that you need around 5 independent slip system to give any arbitrary deformation. So, FCC and BCC, they have plenty of slip system. So, therefore, they are very easy to deform, they can take any shape, they have good ductility. In relation to that, hexagonal closed back structures, they are difficult to deform, and actually so they are not so amenable to any deformation process, and you need extra mode of deformation, that is twinning. And in the next class, we will look at how this does this to deform the crystal, what is the level of stress that you need. And we have seen in a polycrystalline material, we have looked at the stress strain diagram, and we have seen that if you draw the stress and strain, you have this elastic deformation, then you have that plastic deformation. So, there is a stress called yield stress or proof stress. We say that if you exceed this, then there is a permanent deformation. And so, similar thing is there in case of single crystal as well. And in fact, the single crystal, like if you do like this, what will be the nature of stress strain diagram. Now, here is normally in polycrystalline material, these are you have a tensile stress strain diagram. So, here the diagram that we will draw, a shear stress versus shear strain. So, shear stress tau, shear strain. So, here also you will have a similar plot, you will have something like an elastic part, and then you will have a region like this, then you will have a region like this, and then like this. So, that means a typical stress strain diagram of let us say a face centered cubic crystal will have these distinct stages. Now, this period is called you need the stress to exceed this point, and this stress is called critical resolved shear stress. So, when stress exceeds critical resolved shear stress, you have permanent deformation. Permanent deformation. That means, with respect to polycrystalline material, when sigma is greater than sigma y, you have permanent deformation, plastic deformation. So, here, so this is you can say has a similarity, has a relationship between y, sigma y and critical resolved shear stress. Now, you may wonder, so why the slope changes? Now, here the slip takes place, this is called stage 1. You can say that here the hardening, strain hardening is very little, slip takes place on a single system. Here this is a case of a linear hardening region, here you have a multiple slip. And there is again some amount of softening, which says some additional slip planes become operative. So, we will look at these in little more detail, and this is where you need to recapitulate this stereographic projection, because this kind of a stress versus strain plot will be a strong function of crystal orientation. We will see, we will look at in detail the relationship stress strain relationship a little more detail, and we will also look at that during this deformation, does the orientation of crystal, when you pull a single crystal in a stress strain straining device, does the orientation remain same or does it change, and what is the relationship in what crystal, say, depending on its orientation, whether the slip will take place on a single slip system or on multiple slip system. And in the end, we will also try and find out what is the magnitude of, if the crystal is ideal crystal, that means there is no defect, then what is the level of stress, and why we will also have a cursory look why in real crystal you do not have that level of strength. Thank you very much.